Hi there, welcome back. So now let's do an extra step. So this is additional. So we already designed in the previous one our airplane, okay, our wing, sorry. But now let's look at, okay, we find a very good wing, okay, playing a little bit aerodynamic twist, geometrical twist. We find a very good lift distribution, but also we produce the required lift. But now let's take a look at, let us add also the tail. Okay, so we have the wing and the tail. The design is exactly the same. Okay, I will show you that. But, okay, the new thing that we need to do now is we add this tail. Okay, you have the dimensions there. See, everything dimensions. Usually the tail, no vertical and horizontal stabilizer, you have a symmetric airfoil. There is no need to put an airfoil with curvature there. Symmetric is more than enough. And also you can define incidence angle. So let's see what happens when we do this. Okay, we add this tail and see that we have this distance between the wing and the tail. We're defining that there. So we're going to play a little bit with stability. Okay. So I close the my Airfoil. In my case, I see that I saved my project, so I can reopen it. Okay, so always save that project. And let me reopen that. I will launch again Airfoil. Go here, open. You have the project there. And everything that we did in the previous step, you have it saved. You have it there, save it. Okay, so you can visualize everything. Our solution. So remember here, local lift distribution, which was the key 4, or you can go in graph and you have it there. Okay, or if you go to 1, see that this is the induced angle. So if you want to reduce the induced drag, well, you can guess that you want to have a low induced drag, but also a uniform one. So this is the case. See that here we were obtaining that effect. Okay, but we're interested in modifying this airplane. No? So I go here. You have only, let me disable all this stuff. Okay, I don't need it. I want to add the tail. Okay, so let me do here, duplicate and duplicate. I will call it elevator. Okay, I will add the elevator, save it, and then edit the whole airplane. So right click, edit, or you can go here and you edit everything. I go there, whole airplane, and now you need to select elevator. We want to add an elevator. And basically here, see this is the distance. So remember that it was 3 meters. If I will recall, let's open here. So 3 meters plus the core. Okay, 1.4.6. Okay, so this always start from 0. So see that we start the wing from 0, 0. So we add the core, that it's 1.6, plus the 3 meters, which will be 4.6 in X. Okay, so see that you have it there, your elevator. Now you need to give dimensions. Okay, we have tilt angle 0 defined, and now we can create this elevator. So you have the dimensions there. So it is, okay, let me put it 1.5, or let me 1.5. Okay, oh sorry, no, 0, 1.5. Okay, and the core is constant, 0.762, 0.672. Okay, no offset. Okay, no diaeder, no twist, nothing. Airfoil, remember, it's asymmetric, so we need to rerun this case symmetric. Okay, so we have there, see that your definition, and we just need to run for that airfoil symmetric. Okay, so also this one will have a Reynolds number. You need to generate that polar, okay, for that Reynolds number. Okay, so we go when I'm playing Airfoil analysis and design NACA airfoil 0.12, our airfoil. Have it there, I save, and now run the polar. At this point, well, we have the core, you can do your math. I'm just going blindfold here with run one analysis. We'll put here, I know, 2 million. Probably too high. Okay, I run these values and it seems that it's going to crash. Oh no, it didn't crash. Voila. So you have your new airfoil there, and let me go to airplane. Okay, so I go here, modify elevator. Okay, and choose the airfoil, you put it there, and there you go. You have your elevator. Analysis. Okay, you define that. So here you have the wind, no, Reynolds number is not reporting the slow. Okay, well, okay, one thing that just to mention here, let me go back here. Okay, so it run using a different solver. Okay, so let me erase here. So remember that we mentioned that the LLT have some limitations. Okay, one of those limitations is that it's not sensitive. No, it cannot solve the elevators. You have multiple lifting surfaces, the standard one. However, you can correct. Now you know that you have the downwash, so we compute the downwash angle, and usually that downwash will change the angle of this one, so you have the wake there. So no, I don't see the strings here. So you can do that correction, but in XFLR5 it's not implemented in that way. Actually, it doesn't let you run when you have multiple surfaces. So as you define an analysis, see that by default it's changing to one of the other methods. Okay, the vortex lattice methods. Okay, so this one is only for the wind. So here you have the comment. So to run this one, we choose one of these methods. Okay, so use the BL1. Okay, in my case, and we run the previous airfoil just to get the viscous data, okay, because I want to do that correction also, but it is recommended not to have it. So if you disable this, doesn't matter, you don't need the viscous data, but let's enable that, and that's all. So you press run and it will run the simulation. Okay, so let me save using this new solver, analyze. Okay, and we have the data. Okay, so see that it's giving us problems because the viscous data, see that the elevator, it's running at this Reynolds number and we don't have this data. Okay, so we need to proceed in the same way. Now we need to compute at this Reynolds the elevator, the airfoil, and then it will interpolate that automatically. So let me go back here, win, and we can do that design. Okay, so here we have this analysis. I want to do manual one. It's okay, 2.9. Okay, for the 2.9. Okay, analyze. We have it there, all the angles, and likely it will give me problems, so I will run 2.8 and 3 million. Okay, so I got here 2.8, analyze. We have it there, save every now and then, and let me run again define analysis 3. And likely now this is enough information to interpolate that data. Okay, so I just need to do this because I'm using the viscous correction. Okay, so we go wind design, and if I press analyze, it should work. Voila, here we go. So if I go here, see that now we have, okay, let me fuse this data, and okay, I want to see this one, and let me change also the color, and I want this color there. Okay, so see the difference of the data. So the case V5 is the other that we're plotting. We don't have the tail. So the most significant difference here is now with the tail. See that now we are stabilizing the aircraft. See that now we are trimming. So the trim condition now of this airplane is something about 2.5 or let's say 3 degrees, -3. So here is perfectly balanced, okay? But however, at -3, it's not generating enough lift. So see that is quite low. So what we need to do is reach that trim condition exactly when we want the cruise condition. That is, let's say 0 degrees. So I want to reach this trim condition at 0 degrees. So what we need to do is you look at your airplane and this one, just change the incidence angle of this one. So change this incidence angle and that it will push down and it will give more stability. Basically we'll shift to the right this one until we reach this trim condition. But see that also, okay, by adding this downforce here to balance the aircraft, also we're losing some lift. Okay, so actually in our case should be something about 1 degrees that we want that trim conditions. Okay, so you see the effect of adding that secondary lift in the tail. Okay, so that's why it's very important. Always designing, choosing your airfoil, designing the wing, pay attention to the moment, because the moment can destroy your designs. You have a wing that produces too much moment, then it will be too difficult to balance, or not too difficult. You can always balance, but you will need to add too much downforce, or can be upforce. Now it depends how you have everything, or your aerodynamic center, everything in your configuration, and that can destroy your design. Okay, so be careful with that. For us in aerodynamic, we're just interested in the wing. This is just general culture that I want to show you. Also look at that. By trimming the airplane, also we're increasing the drag. So see that the fact that you need to trim, you increase the drag, and this is just induced drag. So if we look at the total drag, you have it there. Okay, so the fact that you trim that, you add that surface, you are adding more induced drag. You are also just adding more viscous drag. But see also that a nice behavior here, that you have it kind of in the same condition. And also we can plot this. Okay, so if I go here, see that we can look at the, okay, let me select 0. You see two curves. Okay, so this one here corresponds to the wing, and this that you see here, it is the tail. So you have the two distributions. So let me go here. So this is the local lift. Okay, here we have it in the wing, but this one, see that CL distribution. Okay, so this one corresponds to the wing, and this is clearly correspond to the tail. Okay, so even if the tail is at 0 degrees, it's producing some downforce due to the downwash. Okay, so if I go here, and this is something nice, again, just visualization. So in this case, this method, we can compute streamlines. So see that you have this action here. So if you select a string, this is only for the vortex, lattice, and panel methods. The LLT doesn't have this information. Okay, we have only one bound vortex, so we cannot compute that. So see that you see here the vortex, and this string slide give you the downwash. So see that this one, you have it there. Basically, this downwash going down is changing the relative angle that this one sees. So we can. That's why in airplanes you have the tail a little bit higher to avoid this downwash. So as we see the design, see that we have here and in the Y. So that what will be the next step to shift it there. Then also we can plot some stuff that in the other one, but what is interesting also is that you can plot the CP on the surface. You have it here. Okay, so see that you select, and this is your CP. One thing about the vortex lattice methods is not like in the panel. You are going to put panels in the surface, and just to make it clear. So if you use the vortex panel in the surface, you put panels. Instead here, this is what you are solving. It is a surface that captures the curvature of the method. It is a huge simplification, but it works. Okay, so we're only interested in resolving the curvature and getting the pressure difference. Okay, this is the BLN. In the vortex lattice, you get the distribution in the whole surface. So at this point, what we want to do is a small modification and shift upwards this one, the tail. So let me go here again. I go duplicate. I call it elevator 2. Edit. I go elevator, and this elevator. Let me put it. Okay, no. I need to go is the whole configuration here in edit, and see that you have also this shifting in set direction. So it will be 0.6. Save, and see that now we have it there, shifted 0.6. So now it's outside the effect of this downwash, or still probably the downwash have an influence, but it's lower. What you see here now, this is the mesh that you are going to solve in the panel method. Okay, see that we have this. So in each one you induce a vortex, that one then you compute the influence in every single panel, and that will induce circulation. In the BLN method, okay, it is just the surface. We don't have the curvature, okay, the camber line that we're solving. So what we need to do now is run this case. Analysis, define analysis. Okay, we have it here, and I'm saying too much, okay. And I put it there, and analyze, and voila. You can put your strings, and we have this. Okay, and now we plot the second case, and let me change the color and put green. So hide that one. See the difference. So the new one, see that we put the airfoil outside of the effect of the wake, and see that now it produces less downforce. Now it is outside that effect, so you have an influence. Okay, and everything is due to that downwash that the tail is seeing. But still, it's not ideal. I would like to trim this airplane about 1 degree, or let's say 0.5 degrees will be my optimal one. But to have it balanced, I need to go something about 0.3. So this is now good. I need to add in the elevator, change the angle. So our next modification is that one. So we go here, and let me duplicate. I will leave that all those cases. I go 3 here. I can edit this, edit elevator. Now I want to edit the whole stuff, sorry. So see here that you have the tilt represents that. So if I put 5, let me see if it, okay, 5 is positive. So I don't want positive, I want negative there. So I will put -2, adding that angle there, and let's see what happens. So having this, analyze, define analysis, boom, 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 there, aero data, and analyze. And everything okay there. If I go here, the polars, now see the new polar. See that now by increasing that angle, now my trim condition is something about 1 degree, but it's still, I want to be something about 0.5. So I need to add more trim, and see that each time that we're adding more trim in the tail, we are increasing now the drag, total drag, and we are losing a little bit lift. Okay, so it's a balance, or the whole design you see is a iterative process. Okay, that is, as you can guess, also if we put here an optimization algorithm, it will work very well. So let's do another, well, in this one, I go here, and let me put -4. Probably it's too much, who knows. Go here, okay, select here, and I run the analysis for -4, and voila. So see that now at -4, see that this curve, first look at the slope is negative. Negative means that it is stable. Okay, so this is what we want, negative slope, and we want to find the trim. This curve must cut this one, intersect this line, the zero moment, okay, very close to your cruise condition. So see that we have it here at 0. Let's say 7, and our cruise condition will be something about 0.7. So this is already an optimal design. And if I look at here, see that my maximum LD is very close to that one. Yes, I increase my drag, but there is no way. So the fact that I need to trim my airplane will increase the drag, but we want something balanced, okay? But if we go here, you can look also at your distribution here, okay? And R, you have it here, lift down this one, and then also you can go and check this one still is, so see that change a little bit here, okay? So probably we can modify this one. So this is also, it will see also the influence of the tail, the wind. So there is an upwash. The tail is producing an upwash that can affect the wind. So it will modify a little bit, but it still is something optimal, okay? So efficiency, okay, it reduced. Well, this is, I think it's looking at the tail actually. Okay, so we go and you check everything, airfoil drag. I don't recall that one, but well, clearly you see this is the tail, this is the wind, and so total angle, okay, and your induced angle. So this is how you do your design. Okay, for us it's very important the wind design, but if you want to go the extra step and your homework, I think it is an optional question, just balance everything. So it's a little bit, you need to play a little bit with these conditions. Something important, I haven't talked about that, but just to mention that everything changes also according to the position of the center of gravity. So as you look at here at this data, you will see that you have something that is called, okay, this one. This is the neutral point. The neutral point is the point about it's like the aerodynamic center. It is independent of the angle of attack. So if I go here, I put my center of gravity here, doesn't matter the angle of attack, always the moment will be uniform, not necessarily zero. So to have a stable configuration, what I need to do is put my center of gravity in front of this point. So it's measured from 0. This is your 0, you have here your neutral point. So if it is in front, it is stable. Ideally, also it should be in front of the aerodynamic center. Recall that concept. So the aerodynamic center, it is 25% of the core, somewhere here, or 25% of the mean aerodynamic core. In case you have feedback angle, it's not located there. So it should be also in front of that point, ideally. So just to show you the influence, or here, when you define the airplane, okay, look at that here, and sorry, it should be okay, in analysis better. So go to analysis, inertia. It's where you define that inertia. Okay, so see, this is the position of the CG. By default, it's always located in 0, 0, 0. So see what happened when I will put it here in the neutral point. Okay, 0.737. Okay. Actually, there is an airplane, 0.737. So if I run now, I just move the center of gravity and high here. You already see that new one. See that the center is the neutral point. See that the moment doesn't change in function of the angle of attack. So DCN over DCAOA or DCCL is equal to 0. It doesn't change. This is the neutral point. Very important in design. So if I put my center of gravity behind this, the airplane will become unstable, and that is not desirable. Yes, airplanes are very sensitive to the position of the center of gravity, at least small ones, okay? Large ones, they are not that sensitive, but it's important to know that. So let me change this one and look at that. I will go here, analysis, and let me move even further this one. I will put it in 0.9. Okay, a new case, analyze. And this is what happens. See that now the derivative is positive. This means that if I add a perturbation to the airplane, it will increase. It's not going to go in a natural way to the equilibrium position. This is very dangerous. So what we want is to have something stable. So as designer, it's very important to know this aerodynamic neutral point, okay, or the aerodynamic center of the whole configuration, and everything is calculated at this aerodynamic stage. Okay, so as an aerodynamic designer, you need to give all this information to the guys doing the stability analysis. So let me go and run an analysis, and let me move forward this center of gravity. So let me put it at 0.25, which it is exactly the same point where we have the aerodynamic center of the wing. So if I put it there, it should be stable. There is no reason why it shouldn't be unstable. The difference, okay, now see that we're in front of the center of gravity of the neutral point, and see that it changed a little bit the stability. Well, a little bit, a lot. So see that now we're trimming about 3 degrees. So if I go to 3 degrees, trimming, see that the moment is 0 at 3 degrees. If I go here 3 degrees, I'm producing too much lift. Okay, so I need to change, or I reduce velocity, or I change the trim condition. So let's change that. So see the strong influence of the center of gravity. So let me go here and let's edit here. And now I want to edit the airplane. Okay, elevator. And instead of -4, let's put -1, probably will be enough. Okay, and let me rerun this case and see that -1, well, probably it's not good. Let's see. So with -1, I need to trim something about 0.5. So probably was better 2. Edit. This car, sorry, is here, the airplane that you want to modify. It's -2. Okay, so it's pushing down the tail. You might be tempted to add an airfoil with curvature. Remember that here in the tail is not recommended. And voila. So see that now we have trimmed something about 0.5 and the required lift, something about that, and see that also the maximum LD, something about that. So see that also when following these rules, this design, kind of everything will fit together. And here, this is how we get an airplane. So we designed only the wing, and then we added the tail using, remember in the tail, we cannot use the LLT method. You need to use vortex lattice or panel methods. As you see, it's very fast. Now imagine running all these cases using CFD. If you haven't done CFD, you will see later that it's very time consuming. Or even if you do experiments, it can be very expensive. So this is the advantage of these methods. And as you see, this is the actual airplane. It is flying. They are very accurate. Finally, what I want to show you, just to also to make it clear, this concept of the aerodynamic center. Let's do it with one of these cases that we have only the wing. So this is only the wing that we have here. And let me show you. So by default, remember, always the center of gravity, it is in 0, 0, 0 by default, but you can change it. So I know that this wing is a rectangular wing, and I know that it is a 0.25, no, the aerodynamic center. So let's see what happens when I put when I put the center of gravity there in 0.25. So let's see that I go here again. Inertia is already there in 0.25. Save. Let's see. I put it there, and let's run here. plot. Okay, still we're a little bit in front, but see that this is the new one, and see that the stability changing, and it have the tendency to become neutral. Actually, it's not 0.25 because the core is 1.6, so 25%, 0.4. Okay, it's 1/4 of the core. So let me run another analysis. If I put it at 0.4, okay, that one should be neutral stability. See that this is what we have. And usually, as I say also, the contribution of the wind, it is to destabilize the whole configuration, okay? Because in the wind, you are going to compute all these moments around the center of pressure, and the center of pressure, it is behind the aerodynamic center, okay? And have this destabilizing component contribution. Okay, so all the case, this is doesn't matter. Designing the wind, remember, by default, it is in 0, 0, your center of gravity. But if you want to play a little bit with this concept of stability and moment, you can switch it. But as you see, the moment doesn't have any influence here. Now, as we change that center, you don't have any influence in this one, okay? That influence, you don't have it here, okay? And just to make it clear, yes, this one. So these two cases is exactly the same. The influence, you are going to see it here. Okay, how you put now this is the R, or the reference length that you use to compute your overall moment. So if you are interested in designing a flying wing, there you have a tip how to do that. So now the flying wing, you need to play a little bit with the center of gravity. So usually you need to put your center of gravity very forward in front of the aerodynamic center. So you put in the aerodynamic center, which is equivalent to the neutral point of the whole configuration with tail. In case you put it in front, you have a stability. So you put it rearwards, it will be unstable, but also you can use a specific airfoil. There are some airfoils that are self-stabilizing airfoils to stabilize your whole configuration. Okay, so that's all. Okay, I don't want to talk about more about stability, but it's important. I hope you get the idea. Stability, aerodynamics, they go together. Okay, so if you do this stability analysis, you need to know all this aerodynamic information. You need to be very good at doing this aerodynamic study. So that's all for this case. In the next video, we'll show you same stuff, but for a taper wing. Okay, so that's all. Thank you very much. See you next time.